Hello, I'm going to be talking to you about how to quantify MagLIF stagnation morphology using the Mallat Scattering Transformation. In addition to the people at the Sandia National Laboratory, myself, Matt Weiss, Chris Jennings, who did the theoretical and simulation work, Dave Ampleford, Eric Harding, Pat Knapp, and Matthew Gomez contributed the experimental images. Also, Stefan Mallat from L'École Normale Supérieure contributed a lot in terms of inspiration and suggestions on how to utilize his transformation. I'm going to start by telling you what is the Mallat Scattering Transformation and why it performs so well in classifying physical systems. Then I'm going to show you the verification of the methodology on a classification performance on some actual stagnation or synthetic stagnation images, and then go and show you how it's actually been used to quantify differences between real experimental images and Gorgon simulations. What is the Mallat Scattering Transformation? It is the convolution or the wavelet what is the 2D Mallat Scattering Transformation is the convolution of kernels at different scales and different orientations. These are the real or symmetric kernels, and these are the imaginary or anti-symmetric kernels with a signal. And that's you can show here is that the signal is X. It is convolved with a lot of these kernels that give a first order scattering transformation, and then it ends up well, this is actually the wavelet transformation, which gets averaged by the father wavelet, and the time coordinate is taken away. You can go, and since a wavelet transformation has time in it, you can also iterate it, take a second transformation, bring in a second scale, and then average that again with the father wavelet. And what you end up getting is then a first order scattering transformation as a function of two coordinates, and then the second order scattering transformation. Here we've taken an image. This is the Fourier transform. We've then gone and put a random phase on it and did the inverse transformation so that the Fourier transforms are identical. The difference between these two images are the phase. You see that the first order Mallat scattering coefficient has is identical really between the two, because that what the Mallat scattering transformation is a windowed scattering transformation, but that there are large differences in the scale-to-scale correlation or the nonlinear behavior of the scattering transformation here. What is the relationship of this scattering transformation to the physics? Well, if we end up starting off with a Lagrangian perspective or a system of ODEs that can be generated from a Lagrangian, a system and what's shown here is a typical system, which is an MHD system that you can go and also show, and there's some work by Burby, that this can be derived from a Lagrangian perspective. Now that this will now go and give you what the system response is, or the state of the system, or the probability of certain states of the system. But then you can go and form a sort of transformation on the state of the system that will now go and give you this canonical perspective, or the scattering matrix, or the generalized Green's function, how one scale scatters into another scale of the system. This perspective is explained in more detail in this archive paper. And so that this Mallat scattering transformation is really the S matrix of the system. You can get a little bit better idea of this by defining the generating function, that is a function of the action on the field as a function of scale. You now go and find out that the Mallat scattering transformation, or the canonical perspective of that, is just equal to the functional derivatives of this generating function. And that ends up being the S matrix, or the way that the scattering cross-section from n minus 1 fields coming in and capital N minus little n fields going out. You can become a bit more physical with this by defining the effective action, and so that you find the first order Mallat scattering coefficient is nothing more than the classical action averaged over the quantum fluctuations or statistical fluctuations as a function of the renormalization scale, and that the second order scattering coefficients is transfer matrix, or the transition rates between one scale to another as a function of the initial and final scales or the scale that you're going from and to the scale you're going to. This also goes and says that it shows you the effective physics as a function of scale, or the physics average at that scale as sort of running coupling constants, or in other words, the renormalization. An example is the phi to the 4 theory, where you can go and write down the specific scattering coefficients. You see it doesn't go above 4th order, and so that you actually have a vertex with an A of lambda 1, 2, 3, and 4 that goes and tells you what the scattering cross sections are going from one to the other. Also, what's really interesting is that you can go and you can identify all of these different physics, or these different stochastic processes, by the functional form, and more specifically by coefficients of those functional forms of the first and the second order scattering coefficients. But let's also go and do something that's a little bit more fun, which is to go and say that if we now go and take the Mallat scattering coefficient and then go and try to reconstruct a signal from the Mallat scattering coefficients, you see that they end up being a very good encoding of the signal. And so I'm going to go and play the original sound next to the reconstructed sound. Now, how are we going to go and parameterize this? Well, we're going to go and take an image, divide it into areas. We're going to take a localized Mallat scattering transformation, or this sort of localized Fourier transformation over each one of these patches. And that's what you see here, really, in terms of the first order scattering coefficients. We also can do the same with respect to the second order scattering coefficients. But it turns out that we don't really need to have all this information. We can just keep these 3 quadrants. In fact, these 3 quadrants tend to look like each other, but with just some systematic changes from one to the other. So we also go and reduce the parameterization from what ends up being 250,000 points down to about 1,400 points. We also ended up forming a series of sort of synthetic images that sort of look like our stagnation, sort of a wiggling single strand helix with things like the wave, and we parameterize these in terms of thetas that give things like the wavelength and the length, etc. of them. Then we also ended up having other stochastic zeta parameters. There are things like the noise, the signal levels, etc. of the images. We ended up forming 8 classes by going and varying one of the the means of one of the parameters by a significant amount, or a factor of 2. And this goes and shows the different ensembles that we ended up finding. So you go and you see, as we go from class to class, there's a real change in the way it works, but you also looks, but then you end up seeing that there's also some small variation around the mean associated with those. What we would then go is find and do sort of an affine linear classifier associated with it. We also ended up and sort of devised, or used and derived regressions for the model parameters from the MST based off of the cross variance of the thetas and the S. In this case, we allowed all of the parameters to vary over a fairly large range. Here you see the linear regression that goes and shows the relationship to things like total length or oscillation wavelength. Here you can go and see that there are portions of other coordinates in it, but it will be predominantly one that's associated with it. And below it, you end up seeing the pattern that you look for in the scattering coefficients. We ended up going and changing, there were quite a few of the design parameters associated with that, and we had sort of optimized the classification performance. Now we ended up going and next ended up using this in order to compare a series of Gorgon simulations across the bottom to a series of experimental data, where we ended up going and just modifying the aspect ratio of the liner for in each one of the different pieces of data, and also the simulations that we ended up having. It turned out that there was a significant distortion between the simulation and experiment. You can sort of go and see that here, and then we ended up forming up sort of the average sort of principal component of the difference between the two to find that as a background. Then we could go and subtract out that background, and we found that the average distance in the transformation space ended up being reduced from about 10 to 20 down to 2 to 5 after we projected out this background. Also notice that the background is at fairly large scale and is in an orientation that's perpendicular to this direction, so it would go in that direction, so that we ended up, this background ended up being a long wavelength sort of vertical striping of the amplitude of the image. After we did this, we were able to go and show that the 4.5 aspect ratio simulation ended up being very close to what the data looked like for the 4.5 aspect ratio experiment. The same ended up being true for the aspect ratio 6. In this case, it was the aspect 6 ratio simulation, which is most like the aspect 6 ratio data. But there was an issue in the simulation for the aspect ratio 9. That actually ended up looking more like the, did not look like the aspect ratio 9 data. In fact, the aspect ratio 9 data still looked more like the aspect ratio 6 simulation.